Today we'll discuss Chapter 16, Marine Geology, the study of ocean basins and coasts. So in the last chapter we introduced oceans and how currents form from temperature and density differences within the ocean and how those currents circulate water through the global ocean. Today we'll discuss more geologic features and how deposition and erosion and igneous rock formation and sedimentary rock formation create the landforms that we see in the ocean. So here we go. We're going to divide up the chapter into first understanding oceanographic landforms and how we study the oceans. Second, into understanding coastal processes like waves and tides, and then third, we'll discuss coastal landforms and their humans' interactions with them. I mentioned Alvin in the last lecture. It is a research submersible that is used to probe the deep oceans, and it's really neat. Consists of a super strong metal sphere in a cigar-shaped tube. And the reason it needs to be really strong is because in the very deep oceans, the pressure surrounding on all sides is immense. And so often scientists like to bring little paper cups that they like to put outside in a sample box outside of Alvin, and the pressure just crushes the cup and shrinks it to a form that's very small and cannot be it cannot find its original large shape again. Bathymetry is the depth of the seafloor, just as the way topography is the elevation of the land. So this image was produced using waves reflected off of the seafloor. This is called the turn of seamount. So what you can see is you can sort of see a broad, flat top to the seamount that's much higher than the seafloor below, colored in blue. Seismic reflection surveys are very important in understanding ocean depths and the rocks that consist beneath the surface. So what you do is you take a big pulse of energy from an air gun and shoot it directed towards the ocean bottom. Some of those waves bounce off and reflect to a hydrophone, which captures the data, and then scientists analyze it to determine the different layers of rocks that are present. So this is called a two-way travel time, and this is used in oil exploration as well as understanding what types of rocks are present under the ocean floor, whether they're igneous or sedimentary, could be either. Here's a picture of the JOIDES Resolution research ship, and this one drills holes into the seafloor to bring up core sections for study. So we learn a lot about the past environments in which the ocean sediments were deposited in these types of cores. We can also learn a lot about Earth's magnetic field and the climate and the evolution of life. So these cores are very important to understand all of these things in the relatively recent history, as far back as when the modern oceans were created, which is about 200 million years ago. The important thing about cores is they show distinct sedimentary layers of the ocean bottom, and they can be preserved for further analysis. So there's core repositories where they keep them preserved very well in different universities and governments around the world. If we were to refer back to our lecture on mid-ocean ridges and plate tectonics, then we'd understand that oceanic lithosphere is denser and thinner than continental lithosphere or continental crust, and it forms deep ocean basins. So the continental margins can be both passive or active, depending on whether there's some crust that's being subducted beneath it. This would be active, or if it's part of a plate that is spreading on from the outside, and the continent is being pushed towards another direction, and this would be passive. So if you think of the United States, the east coast of the United States is a passive margin. There's no active subduction, there's no volcanism or mountain building going on currently, and that's because the middle of the Atlantic Ocean, there's new ocean crust being created, and that the North American plate is being pushed along with that ocean crust towards the west. It's also being pulled. Well, no, I won't say that, but anyway, it's being pushed towards the west. On the west side of the United States, the western coast, the Pacific Ocean is going underneath or subducting underneath the United States. This is an active margin. We can describe ocean bathymetry through bathymetric provinces. The shallower realms include the continental shelf, slope, and rise, whereas seaward from the continental shelf, the continental rise is the abyssal plain. Broad continental shelves form along continental margins, so this would be the case in the Gulf of Mexico and in the eastern U.S. Then we have things like Goyets, seamounts, and oceanic islands. Those are volcanic, as are the mid-ocean ridges. Then on the right of the figure, we have a trench and a volcanic arc. This would be the case in a convergent margin where we have subduction of the oceanic lithosphere. So we've got passive on the left, we've got the creation of ocean crust at the mid-ocean ridge, and then we've got active on the right with the volcanic arc and trench. Goyet, seamount, and oceanic island, these can exist in any place as a result of hotspots, activity, or they can be close to mid-ocean ridges as vestiges of the mid-ocean ridge volcanism. So here's a picture of the eastern coast of North America, where you've got the broad continental margin, or broad continental shelf extending beyond the continent. So this is shallow water extending for a good while out into the ocean. And so the reason for this is because there's a sediment-filled basin, or a sediment-filled depression called a passive margin basin there. And so this forms from the stretching of lithosphere, which has cooled and sinked, and that basin has accumulated sediments. Active margin continental shelves, as you can see on the figure below, are much thinner and have a trench. So this would be the western coast of South America looking south. So we have the Atacama Desert going through the going with the line, the cross-section line going through the Atacama Desert there. And also there are things like accretionary prisms there, which are wedges of sediments that have been scraped off the seafloor during subduction. Submarine canyons exist all over the place, and they produce these submarine avalanches known as turbidity currents, where these turbidity currents have all sorts of different sizes of sediment falling down them, with the heaviest sediment falling the fastest and landing first, and then the lightest sediment landing last. So you get this sort of graded material where you go from very coarse to very fine in a turbidite deposit. Here's a mid-ocean ridge and a fracture zone associated with it that's producing some offset where the mid-ocean ridge has jumped. We have shallower water at the ridge crest because there's hot mantle crusts, buoyant magmas that are rising underneath it, and then as the magmas cool to form rock and get pushed out on either side to the left and right or the west and east respectively, this ocean floor gets deeper. So here's the picture, satellite image of the Mid-Atlantic Ridge. Here's a cross-section photo of the picture I just showed, with the crest being higher and having shallower water above it than the abyssal plain on its sides. So the abyssal plain includes also sediment, which gradually accumulates and covers the basalt of the oceanic crust, and this forms kind of a flat, pretty much featureless surface. Here's a picture of some oceanic islands and seamounts which rise above the abyssal plain or mid-ocean ridges. So you can see they're kind of all over the place and result from hotspot activity. Seamounts, tops may be flattened by erosion, which produces something called a goyet, which would be similar to like a mesa on the land, except for the goyets are from igneous activity and mesas are formed from sedimentary rocks. So here's a picture of the OJP, which is known as the Ontong Java Plateau, a large plateau of volcanic material that was exploded underneath the water, and there's a lot of seamounts associated with it. This is near Oceania. Now we'll discuss tides. This is the beginning of part 2 of the lecture. So tides are generally twice daily rises and falls of sea levels generated by the effects of lunar gravity on Earth. At low tide, sea level falls to its lowest elevation, shown on the picture on the left. At high tide, sea level rises to its highest elevation, which is the picture on the right. This is actually the same location, different times of day, at the extreme low and extreme high tides. The tidal reach is the vertical distance between low tide and high tide. Here is a picture of a French harbor at low tide with some equipment that will allow the boats and walkways to rise safely at high tide. The intertidal zone is the surface of the seafloor that lies between the shoreline at high tide and the shoreline at low tide. This is the horizontal distance that the tide rises and falls. Where in places where the tidal reach is large and the beach slope is gentle, the position of the shoreline can move by kilometers during a tidal cycle, exposing a broad tidal flat during low tide. So here's a picture of a tidal flat with some boats that are on dry land as a result of low tide. A tidal bore is the arrival of flood tide in the mouth of an estuary, where the tide moves against the river flow and this produces a tidal bore. So this is a visible wall of water that moves up at speeds of 35 kilometers per hour. Here is a picture of the Bay of Fundy, the east coast of Canada, which has the highest tidal range in the world. The tide generating force is a combination of forces that causes tides to occur. So these include the gravitational attraction of the moon and the sun, and the centrifugal force caused by the revolution of the Earth-Moon system. This produces two bulges in Earth's water, called the sublunar and secondary tidal bulges. The larger sublunar tidal bulge always faces the moon, and the smaller secondary tidal bulge is always on the opposite side of the Earth. So the larger tidal bulge or sublunar bulge is shown in the top photo, and the secondary bulge is shown on the opposite side of Earth in the top photo. If we want to view this from the side, the sublunar bulge does not align with the equator because Earth is rotated and tilted on an axis from vertical of about 23 degrees. So the high tide is somewhere between the equator and the 45-degree mark. When the sun is aligned with the moon, stronger higher tides called spring tides result. This doesn't refer to the season, as there are 2 spring tides in every lunar month. When the sun is at the right angles to the moon, weaker lower tides result, called neap tides. So here's a picture of a spring tide on the top photo, and then neap tides on the lower photo. These can add or subtract to the daily high and low values of high tide and low tide. We spoke of waves in the last lecture, but we'll go into more detail today. Waves interact with the shoreline to create a number of phenomena called breakers, surf zone, wave refraction, and longshore currents. Breakers are what people think of typically as waves that aren't scientists. So near the shore, the wave base interacts with the seafloor, slowing it relative to the higher portions of the wave. This causes the upper part of the wave to curve over in its base and become a breaker. So this is how waves break. So waves are present in the ocean in all locations near the surface. However, it's just when they start to come closer to the shore and reach those shallower areas that they'll start to break and turn into the waves that people are more familiar with. Breakers break in something called the surf zone, which sends a surge of water onto the beach. And this upward surge, also known as swash, continues until friction and gravity bring the water that's in motion to a halt. and then gravity draws the water back down as the beach as backwash. So whenever you go to the beach, know that this is gravity pulling the water back in after the crashing of every wave. Waves approach beaches at angles, bends, or curves in a phenomenon known as wave refraction. This tends to swing waves around to be more parallel to the shoreline. And waves still tend to reach the shoreline, however, at oblique angles and can sometimes create longshore currents that moves parallel to shorelines. And this actually moves a lot of sediment on a daily basis from certain parts of shorelines to either a northern or more southern locations on the same shore. Rip currents you may have heard of if you've been to the beach or lived at the beach. These are dangerous currents that form when backwash concentrates into narrow local currents that carries water further offshore. So there's a picture of the rip current, and if you get caught in one of these, the idea is to swim parallel to the wave break on outside so that you can, rather than fight the current, but as you get transported out, swim parallel and then try to find another entrance back into the shoreline. Beach sediments are made up of different types of sediment because there are different sources for those local sediments that erode and create the sand. So quartz sand often comes from the erosion of felsic rock, carbonate sand from the fragmentation of cells, and black sand from basalt from volcanoes. Here's a picture of a beach profile with several distinct zones. You got a foreshore zone that includes the intertidal zone as well as the beach face. Then you've got a backshore zone which extends from a small step cut by a swash to the far edge of the beach further inshore. So you've got the wave, you've got shoaling zone, nearshore zone, foreshore, backshore. Then you've got beach cliffs and dunes. Then beyond the beach cliffs and dunes you have marshes, lagoons, and mainlands. Beach width is the area with frequent wave actions and can vary seasonally. So on the left we have a narrow beach in the winter, and then on the right in the summer we have a wide beach. This is typical because in winter strong storms move sand offshore, and in summer gentler waves can carry sands back to the beach. Longshore drift occurs as swash carries sand obliquely upslope on the beach, then backwash carries it straight downslope. So we've got a wave refraction not perpendicular to the shoreline, moving sediment in the red arrows, and then the sediment coming back down to gravity that is perpendicular to shoreline in the blue arrows. Over time, this moves sand in the direction of the longshore current. It forms a sawtooth pattern. Spits, bars, and barrier islands are geomorphological features that form in coasts. Sand spits form where a coastline indents and the longshore drift extends a beach out into open water. And if spits grow across an open bay, it forms something called a behemoth bar. Where there's abundant sand and a gentle slope, a barrier island may form. Lagoons are spaces of quiet water that are between barrier islands and mainlands. These are salty waters. Here's another picture of a tidal flat, especially broad, nearly horizontal area of mud and silt that is exposed or nearly exposed at low tide and submerged at high tide. So this very famous example is from Mont Saint-Michel in France, which is a monastery that individuals drive out to in low tide and must drive back from in high tide, otherwise their cars will be taken away. Sediment budget is the balance between sediment supplied and sediment moved. So sediment originates from river discharge or erosion on land, and some sediment moves along the coast by longshore drift, and some of it washes out to sea or goes down submarine canyons. Wind may also blow sediment inland. So the net transfer of sediment from land to sea is known as the sediment budget. We'll discuss a few more coastlines here. So here are rocky coasts. These lack protections of beaches and feel the full impact of ocean breakers. Wave erosion can gradually undercut cliff faces, causing eventual toppling of overlying material into the sea and subsequent cliff retreat. Features include wave-cut platforms, headlands, sea stacks, sea arches, tombolos, and embayments. All of these are formed from erosion, and are at different stages of eroding a particular rock face. Wave erosion gradually undercuts cliff faces, causing the eventual toppling of overlying material into the sea and subsequent cliff retreat. So this produces wave-cut notches and wave-cut platforms. Headlands and embayments often occur on rocky coasts, which over time waves tend to erode these away, producing sea arches and sea stacks. These temporary features are eroded away over geologic time. Estuaries are river valleys flooded by sea level rise. For example, the Chesapeake Bay in Virginia. Fjords are flooded glacial valleys carved most often during the Pleistocene Ice Age. Coastal wetlands are a vegetative flat-lying stretch of coast that floods at high tide and becomes partially exposed at low tide, but does not feel the impact of strong waves. Coral reefs are made of corals, which are tiny living invertebrates that build mounds of stony materials in various shapes and sizes. Coral polyps secrete calcite shells that gradually build into a mound of solid limestone. These are colonial animals. Reefs of the world occur in tropical waters between 30 and 30 degrees north and 30 degrees south latitudes. There are several types of reef shapes, including fringing reef, barrier reefs, and atolls. Fringing reefs form directly on coastlines, barrier reefs lie offshore, and atolls are circular rings surrounding lagoons. Here's a timeline of the evolution of Pacific Island reefs. So fringing reefs formed around an island, first off a young volcanic island, which exploded and built up more land. Then continuing growth occurred, forming the barrier islands around. Atolls formed slowly as the island was no longer spewing volcanic material, and the volcanic material eroded. So here's Moorea Island in stage 1, Bora Bora in stage 2, and the Maldives in stage 3. Emergent coastlines are coastline locations where the land is rising relative to sea level. This creates wave-cut platforms and terraces. So here's an active beach, wave-cut platform at sea level. As the land surface rises, we get a terrace because we get the active beach at a new location. Submergent coastlines are where the land is sinking relative to sea level, which creates estuaries and fjords. Erosional coasts are where wave action washes sediments away faster than it can be supplied, creating coasts that recede and become rocky. Accretionary coasts are coasts that receive more sediments than they do lose by erosion, grow seaward, and develop broad beaches. Now we'll discuss coastal storms. Storm surge associated with coastal storms causes a sea level rise locally and briefly that is independent of waves and tides. Storm surge can inundate land far inland with associated backwash and can remove vast amounts of sand from beaches. Here's an example of Galveston, Texas before and after Hurricane Ike. Ongoing sea level rise estimated to be about 3.2 millimeters per year, and these areas pictured below are likely to be flooded if sea level rises by 1.5 meters. Various factors can destroy beaches, including storms, loss of river sediment supply, gradual sea level rise, changes in the shape of the shoreline, or destruction of coastal vegetation. Some examples are at Cape Cod on the left and Palm Beach, Florida on the right. Last part of our lecture will discuss beach protection. So it's the human relationship with the beach. These beach protection measures include groins, jetties, breakwaters, seawalls, and beach nourishment. Groins are concrete or stone walls perpendicular to the shore that prevent longshore drift from removing sand from beach. So here's a picture of a groin with wave action acting on it before and then afterwards. What happens is, as longshore drift occurs, imagine it's moving to the top right, that water, the waves get blocked by the groin, and the material gets deposited on its left side, whereas beyond the groin there is erosion and there's no wave action to deposit the energy on its right side. A jetty is a pair of perpendicular walls at the entrance to a harbor. Jetties effectively extend a river channel into deeper water, which may lead to deposition of an offshore sandbar. Breakwaters are constructed offshore, parallel to the shoreline, to prevent full force waves from reaching the beach. Seawalls are built along the shore out of riprap or concrete. Seawalls can protect the shoreline in many conditions, but can be undermined during severe storm conditions. Beach nourishment or beach replenishment involves replacing sand that has eroded away. This can be very expensive and often only provides a temporary fix. Lots of pollution problems in our oceans. For example, ocean ship transportation of waste and fuels carries the potential for spills, resulting in ocean and coastal pollution. Longshore drift can carry this pollution great distances, and oil spills from ships and tankers can travel great distances on ocean currents. Organic coasts are susceptible to changes in their environment, including from sewage discharge, chemical pollution, agricultural runoff, coastal development, seawater temperature changes. Here's an example of bleached and mostly dead coral reef in the Caribbean.